Today we will be covering chapters 4.1 and 4.3, critical points, and min-maxing. Okay. Okay. Let's get right into it. I'll throw some definitions at you. So our first definition is going to be the definition of a critical point, which you might see me shorthand as critical point. Okay. Or CRTPT, whatever. Okay. So let f of x be a function and f prime x be its derivative, its first derivative to be specific. Okay? For all, that's what that means for all, x naught such that f prime of x naught is equal to 0. X naught is, oh, I should cut that out. X naught is a critical value and the point x naught comma normal f of x naught is a critical point. You might see me use like this whole thing and just the x naught interchangeably as critical point, but usually when we say critical point, we want it as an ordered pair. Okay? Note, do not give me x naught comma f prime of x naught. Why? F prime of x naught is going to equal 0. Always. Because that's how we defined it. Okay? Do not give me f prime of x naught as your y value. Okay? Always f of x naught, the original function. Okay? We'll show you why it's important in a second. Because you'll have this next definition, local min or max. Okay? Again, we go back to this original definition, right? We say, let x naught be a critical value. Let x naught be a critical value of f of x, right? Let epsilon be some value greater than 0, just a number. Okay? If there exists an epsilon greater than 0, right? Such that f prime of x naught minus epsilon is greater than 0, sorry, less than 0, and f prime of x naught plus epsilon is greater than 0, which is to say very specifically that to the left of x naught, f prime is negative. To the right of x naught by some tiny value, right? F prime is positive. Then x naught comma f of x naught is a min. It's a minimum value, okay? Similarly, if there exists an epsilon greater than 0, such that f prime of x naught minus epsilon is greater than 0, and f prime of x naught plus epsilon is less than 0, then x naught comma f of x naught is a max. That is to say, to the left, positive, to the right, negative. Okay? So, I'll show you a picture, and then I'll show you a more practical definition, okay? Or a more practical way of looking at it. So, let's say that our graph, right? And let's say that this is your f prime graph, right? Well, we know, just by looking at this, that this right here is a critical point, right? Now we're going to choose an epsilon. Again, epsilon's just a number. Who cares what that is, right? Let's say you choose your epsilon to be like, I don't know, like, let's call this like, I don't know, 7, right? So there, right? X value is 7. And let's say this is a distance of 3, right? And that means you're going to go this distance of 3 on the other side as well, right? That gives you 7 minus 3 is 4, 7 plus 3 is 10, right? If you can do this, right, on the left-hand side, we have, let's see, this goes up, up, up. So you have 4 comma f of 4, right? Which is 4 comma some positive number, right? Because you're above the x-axis, right? On this side, you have right here 10 comma f of 10, sorry, f prime of 10, right? These are primes, right? And this is going to be 10 comma some negative number, right? If you ever, for whatever god-awful reason, take analysis, they call this an open neighborhood, okay? It's not important what that means. You can kind of view it as a little bubble, right? What that means is if on the left half of the bubble you have a positive output, and on the right half you have a negative output, right? Then that means that, oops, then f of x, the normal f of x, has a, let's see, increasing to decreasing max at 7 comma f of 7, okay? And what that means, and the reason why this works, is because what you're telling me is your function is, let me do it in hot pink. It means that your function on this half is increasing, right? Actually, let me do it in like green. It's increasing, right? Do you notice how the slope here is positive? And then the slope is 0. See, slope here is 0. Pink is a slope function, right? Positive slope hits 0, right? Positive slope, 0. It doesn't matter if the positive slope is going down. If it's above the x-axis, it's still positive, right? And then on this side, negative slope. Negative slope means decrease. Ta-da! Means you have a max. Positive, 0, negative. Ain't that beautiful? Okay. Let's do another one. Actually, let's not do another one. Let's call it a nice and applicable definition. Okay? Your max is when f prime of x goes from increasing to 0 to decreasing. That is to say, the derivative function goes from up here, and then it hits 0, and then it goes, let me do that in a slightly different color, and then it goes under. Does that make sense? In the same way, you have, oh, and this is your max, of course. Your min is when, actually, let me just turn that down a little bit. Your min is when f prime of x goes from negative to 0 to positive, okay? This is where the mean value theorem comes in. You're saying like, oh, well, you go from positive, oopsies, function's continuous, and you go from negative to positive. That means you have to hit 0, which means at some point, you have a min. That's literally why we teach the mean value theorem, more or less, okay? And picture-wise, that means function goes from like, let's see, negative, and it hits 0, and then it goes positive, right? That means that your original function, f of x, has a max, has a min at whatever this x value is, okay? Big picture, we want to use a sign chart. And I'll show you a fun application of it, okay? So suppose we already found a derivative, right? Let's say f prime of x is equal to x plus 1, x minus 1, right? Okay. This is what a sign chart looks like. Know that f prime x equals 0 at x equals positive and negative 1, right? So we'll put negative 1 here and positive 1 here. Okay, we're going to start picking some numbers. Please pick nice ones. Okay, so we're going to start over here. I'm going to call this like quadrant, not even a quadrant, section A, right? Pick a number that's nice to work with in section A. My personal advice is if one of your sections head towards positive and negative infinity, choose like obnoxiously big numbers. Okay? For this one, for section A, I'm going to choose like negative 100. Okay? So f prime of negative 100 is equal to negative 100 plus 1 is going to be a negative number. I don't actually care what this number is. Okay? Negative 100 minus 1 is definitely going to be a negative number. Don't care what that is. A negative times a negative is a positive. So I know that beyond here, your function is going to be increasing because its derivative is positive. Okay? In a similar way, I'm going to choose, let's call this section B. For section B, I'm going to choose a nice number. Don't choose like negative a half or like a positive half. Choose 0. Okay? If you can, choose like 0. So f prime of 0 is going to be 0 plus 1 is positive. Also, this is why factored form is nice, okay? 0 minus 1 is negative. Positive times a negative is a negative. So we know that from negative 1 to positive 1, our function is decreasing, right? And then for section C, right, I'm going to choose positive 100. So f prime of 100 is equal to, if you want, you could totally actually plug the values in and calculate it out. That's fine. It's perfectly fine. I don't care. Okay? I'm not going to because I'm lazy. 100 plus 1 is a positive. 100 minus 1 is still a positive. And that's going to be positive. All right? So this function, the normal f of x, is going to have a positive to negative. So that's a max. And a min, because it goes from negative to positive. That's it. Easy money. Obviously, I won't always give you f prime. Sometimes you'll have to find it yourself. I'll give you the original function. Okay? Yeah, that's it. The last definition I'll throw at you is global, min, and max. So again, let f of x be a function and some interval. It could either be like a comma c like this, or a comma c like this, or like a comma c like this, or a comma c like it doesn't matter. Okay, it doesn't matter is the point. Okay, let x naught, x1, all the way to xn be maxes of f of x. The global max of f of x in the interval. So any options of these, any combination of those, is the f of xi. So like any of these, whichever the one that is greatest, such that xi still lives inside your interval. Okay? So for example, let's say that actually, yeah, let's do an example. Let's say that this is your function. It's like, wee, right? And then actually, you know what? Do another one. There we go. Right? And your A cuts off here, and your C cuts off here, right? And you have maxes at here. Let's call this J, K, and L, right? Which one is the global max inside your interval? Well, you're not going to look at this guy because he's outside, right? What you're going to want is to look in here, whichever one is highest, whichever one has the highest y value, right? The y value of this point is lower than the y value of this point, right? So k is going to be your global max. That's it. Similarly, right? Your global min is the lowest minimum value in your interval. Okay? Now, let's make a note. if A or C is included in your interval, check their y values too. So for example, right? This is our chart, right? And we're looking for mins. Okay. We know that we have a min here, right? But this min is still higher than this. So, out of the question. We know we have a min here. Okay. But we know that A is also included, right? We have to make sure that this doesn't happen to be lower than this, even if it's not like a critical point and gets a 0. Okay? You might hear me say this as check your endpoints. Okay. So, what I'm going to have you do is do problems listed in my notes, solutions to come later. All right. Thank you for your attention.